may not know where is the source. Like we hear some voice or noise, we don't know where the source of the wave, or we don't know the conductivity, and we don't know the material property. So that in that case, we want to use the observable information, could be directly some part of the solution from the PDE, but could be a function of the PDE. For example, if I'm solving Boltzmann equation and I won't be able to get very microscopic behavior, but I can get temperature or some other like micro behavior. And we use those information that can be observed to infer, to use some method to reconstruct what is the boundary and what is the material property. And those those methods especially popular in modern medicine. For example, X-ray, CAT scan, MRI, and ultrasound are all examples of inverse problem. And in those medical procedures, what we try to reconstruct is the media where the wave propagate, where the machine of X-ray or CT, they serve both as the source and also as the receiver. And some programs will try to do the imaging at the same time. So inverse problems are everywhere. And nowadays, more and more problems we start to think about, for example, Boltzmann equation-based inversion. And here I just want to try to describe some inverse problem as one example. And this is what I call like most classical inverse problem. It's called the Cadron's problem. The forward modeling is this elliptic PDE. And the inverse part or the parameter we are interested in is this conductivity gamma. We are now interested in solving U, but really use some information from observable from the boundary, try to reconstruct gamma of X. And for that problem, there's a lot of study on the existence, uniqueness, and the well-postedness. But in the end, when we try to do some reconstruction, some variational approach would be very helpful if we do not know the inverse map, etc. So for example, here I list a very classical paper by Bob Cohen, who will give a presentation later in this workshop, and also Regulus on the relaxation using variation method for EIT or for Cadron's problem. And that was the starting point. And also many variational or data fitting type of approach for solving this inverse problem follows afterwards. And another one which I'm very familiar with is this wave inversion. So earlier the medical procedure is like doing wave inversion on the body tissue, but here we are doing wave or ultrasound on the entire Earth. And in this problem, we know the source, we know the boundary and the initial condition, but what we don't know is what's going on underneath the Earth. So we want to reconstruct material density or velocity. So that's another very challenging nonlinear inverse problem. And again, to solve this problem, finding the exact map from M to U or from U to M is not practical, especially consider the scale and the nonlinearity in it. A practical way to deal with that problem is to formulate it as a PDE-Constrained Optimization. Try to minimize what I can observe versus what I predict, and try to use optimization algorithm iteratively update the parameter. And another inverse problem which I started to look at recently is this Boltzmann equation. So Boltzmann equation is known to have a very high dimension as a forward problem, but also have very important application value in practice. For example, I want to do a shape optimization for the gas flow, or I want to design a semiconductor device, or I want to use this model to do some quantitative finance. You may all involve Boltzmann equation. And in that case, not only we are concerned with solving the forward problem, we also are concerned with how to solve the inverse problem accurately. And for this one, we want to reconstruct what is the boundary. So the boundary is unknown, or the shape is unknown, and we try to do it by minimize an objective function through a data fitting approach. So in all those three examples, and many more inverse problems, the practical way of solving it is turn it into an optimization approach, and that's commonly shared by optimal control and many data science like the keywords in our workshop. So instead of searching exactly what is the inverse map from D to M, we try to formulate it as a constraint optimization. So based on some information we can observe the data, usually we regard it as the data in the narrative. So based on the data we can observe, we can also try to simulate the forward process based on our own guess of the parameter M. So M in EIT will be conductivity. In wave inversion is velocity, and in shape optimization, that will be the boundary. So in different problems, that will be a different M. But in the end, we formulated as a process doing data fitting. So fit the observed data with our synthetic data. So although the objective function is data fitting, but our ultimate goal is to reconstruct the correct velocity. So this is a constraint optimization, and also the gradient flow will also be a constrained gradient flow. So this adds a lot of difficulty and also interesting problems in this field. So it's very nice since it started to utilize in all different inverse problems, because nowadays I don't have to really to think about what is a highly nonlinear maps inverse. And I only need to solve the forward problem, which is numerical solution to PDE or ODE, which we have studied for several decades. And for linear problem, for example, linear regression, it works really well. And there's a lot of foundation in statistics and application. But at the same time, this formulation reduced the difficulty of the original inverse problem, but also add certain, and also have its challenge by itself. For example, the parameter we want to search usually is a parameter in PDE or ODE, and they belong to a certain functional space. And if we formulate it directly as a deterministic inversion, that once we discretize, we turn it into a finite dimensional problem, and that's no longer the original infinite dimensional problem. And the ill-posedness of the inverse problem, like existence, uniqueness, and stability, still get reflected in this PDE constraint or other ODE constraint optimization. It is reflected most likely in the non-convexity part. And a third problem is really, a third difficulty I can see is really problem dependent. It depends on how expensive it is for us to simulate the synthetic data. If it's really easy, just a matrix vector evaluation, that's okay. But if it's like, say, solve a wave equation, and I need to do time marching in each iteration for like several 30, 40 kilometers, that won't be very, that will take a lot of time, and that also the constraint for this formulation. So what I'm going to talk about is some methods we propose to tackle some of the challenges. And for PDE constraint optimization from inverse problems, or PDE constraint optimization from optimal control, or the nowadays machine learning, I would consider all of them fit into this diagram. We have an input data, and the data usually in pairs. And in supervised learning, it will be my X and Y as my data. But even for PDE constraint optimization for wave inversion, I also have such X and Y. For example, X can be my particular choice of source, and Y will be my produced wave solution. And also correspondingly, X can be my boundary condition for the elliptic cadence problem, and Y will be the measurement I get on the Neumann data. So for all such problem has an X, Y, and the X goes through certain model, can be PDE by doing the forward simulation, can be neural network doing the forward propagation, or it can be others. And we generate Y, and in the end, we minimize the true Y versus the synthetic one. So if all those important problems we care about are formulated as such a constraint optimization, is the optimization part, then J is really very important. The objective function is very important for us, because now in order to find the correct parameter, the only indicator I have is the loss function. So originally, maybe if I'm just comparing the entire data set versus the entire data set, I have a lot of information. But once I turn into a constraint optimization framework, what the only information we have nowadays is the objective function and the corresponding gradient based on this objective function. So objective function play a key role in many of such problems. For example, for the wave inversion, the traditional objective function has been the least square norm. And the least square norm, it's usually the first choice we go for, no matter which inverse problem or regression problem we want to deal with, because it's very easy to compute the difference, and also very easy to calculate the gradient. So here we have synthetic data F that depends on the model parameter and the true data G, and depends on which domain they are defined in. So this is in L2 norm in both time and the spatial domain. So particularly for wave-based type of application, this is not a very robust choice. And since it was proposed by Tarantola in 1982, people already realized most likely I suffer from some difficulty when I do numerical experiments. For example, if we have random initial guess, most of the time, the initial guess won't drive me to the global minima as a sum of trapped at the local minima. So that's one thing, because especially the three examples, the inverse problem example I give you are all nonlinear inverse problems. Means the dependency or the map from M to the data, and also vice versa from data to M. If they exist, they are highly nonlinear. And they are highly nonlinear, and we put it into a least square formulation. They won't be quadratic. They won't be very convex as a linear problem will give us. So naturally, it's possible to get a lot of local minima. And the second challenge that we encounter most of the time, which I regard as shared by all least square-based formulation, is the lack of robustness with respect to noise. So if my true data G I observe from the field or from other procedures, other machines, if the G is polluted by different kinds of noise, by wind, by wave, or by the measurement device noise, then that noise is inevitably fitted by my objective function. So my objective function easily can see that noise. And if my objective function can see that noise, then my optimization framework will also try to fit that noise. And that's what we call very often the overfitting phenomenon. So that's another well-known challenge, but that challenge could be sometimes mitigated by adding a regularization. So if we want to have the optimization to be more robust with respect to noise, we add a regularization. And a Tikhonov regularization or TV regularization are well-known choice, depends on our prior information. So that's the certain challenges, although I was motivated by the wave equation-based inversion, but I believe such challenges really persist in many different nonlinear inverse or nonlinear fitting problems, including machine learning, including EIT, and including Boltzmann-based inversion. So our approach to deal with the challenge, particularly for wave equation, come from the assumption that our recognition that it is a data fitting approach, but our ultimate goal is not data fitting. Our ultimate goal is model fitting. So it's very important for us to understand the dependency, how my model parameter perturb can cause my data side that I can observe perturbation. So we see that from this 1D wave equation to get some insights. So this is a constant velocity wave equation. And we learned that in PDE, we can represent the solution by the D'Alembert formulation. So one of the solution can be expressed based on the boundary condition f of t. So I can write it down, the entire solution depends on f and also depends on my constant velocity m. So in this simple case, I can see directly how the change in m, which is my parameter I want to reconstruct, versus the data I can observe at a certain location or at a certain time. So for fixed location, if I fix the location and observe the data, variations in the velocity give me translations in the signal. So if M get perturbed, what we can observe, it will be a translation of the true data. And for fixed time t, perturbations in velocity parameter will cause dilation in the signal. It depends on how you choose to observe your data. But this also indicates that when I do not have the correct parameter, what I see from the data set will be translation and dilation. So if I want to use an objective function to do this data fitting, I want my objective function to capture that, since those transformations are direct consequence of incorrect model parameter. And I think we should bear this this line of thought for dealing any inverse problem that you want to reconstruct the parameter accurately. So since once we realize that, the next question to judge is whether the least square norm, or the general LP norm, is a good candidate to capture such global, non-local transformations? And the answer is no, because LP-based norm, LP space, they are very point-wise comparison. Here we have a numerical example. If we consider the blue signal as the truth, as the reference data, and the red signal is a translation of the blue signal. And the translation can happen very often, especially in wave inversion that I want to reconstruct velocity. For fixed distance, if I guess it, if the truth is 2 kilometers per second, I may arrive after 6 seconds. And if I guess it's 1.2 kilometers per second, and I may arrive much later than the truth. So translation are direct cause of incorrect velocity. And the next, I compare the differences among these two signals under LP or L2 norm. So when they overlap, we have misfit 0. But as long as we start to have any mismatches, we see a lot of local maxima and local minima. And if that means if I use gradient-based inverse optimization algorithms, easily we can get stuck at those local minima and won't be able to jump out of it by deterministic optimization approaches. And that's the limitation of LP-based norm because it cannot capture the basic translations. But alternatively, if I use the quadratic Wasserstein distance to compare the two signals, everything else remains the same. The only thing we change is the objective function. The optimization landscape look radically different, which is the picture on the upper right. So we get a globally convex optimization landscape, and it's order of shift square. So this is a much better optimization or objective function we want to work with, especially if local optimization algorithms is what you rely on. If your problem is large scale, it's impossible to do global optimization. Then you want to search, you want to gain convex or more convex optimization landscape. And that's also take us to the second part of my talk, optimal transport. I'm not sure what the audience, but I would just give a brief overview of optimal transport. So optimal transport is also part of the workshop's keyword. And I believe in the following talks, you will see a lot of many very interesting and impressive applications of optimal transport in applied mathematics. So optimal transport is not a new subject. It's a very classical analysis subject started from Munch in 1781. Munch have this problem that I have a pile of sand. I also have a big hole, and they have the same volume. And the next, I want to move the sand to the hole. And here, there's the problem that I have so many different choices. I can move the left to the left, the right to the right. So that's one way to do it orderly. Or I can do the right to the left and the left to the right. So this is just two different ways. And because it's some domain, we have infinitely many different ways. So Munch's problem is which way give me the smallest cost, and that will be my optimal way to go for. So the original formulation of Munch's problem is searching for an optimal function. It's an optimal map, which is a function. So he is searching in a functional space. So the dimensionality is large, it's an infinite dimensional optimization problem. And at the same time, it's a nonlinear formulation. So you can see there's not so much going on for 200 years almost until in 1940s, Kantor-Ravitch relaxed a little bit. If I do not search for function, if I search for plan, which means I allow X, position X, some mass to map to both Y1 and Y2. So we break or we violate the requirement for a function, but we gain something, we relax the problem. And he formulated it as a linear problem. So it can be solved numerically by linear programming. And he pushed it to economics and also earned himself the Nobel Prize in economics in 1975. And in late 20th century, there's a lot of fruitful results in pure analysis of optimal transport of this problem, also around the related PDEs for this problem. So I would say at the beginning of 2000, the solid foundation in theoretical side for optimal transport is quite solid, it's quite well, and that also naturally boosts certain applications since 2000. The first era embraced this idea is computer vision image processing. And the recent 5 years, you see GAN model, which you will hear very soon, that optimal transport has particular advantages. And from my side, that I can see more often is to use it in inverse problem. And recently, there's I know somebody at Courant also use it for model reduction for hyperbolic equations. And that is a very innovative idea. Maybe the traditional Sobolev norm won't be the best choice for do model reduction, but doing model reduction under the Wasserstein space exactly capture the dominant transport part. So there's a lot of application, and I believe there are more beyond this. And also the connection with other fields is impressive. So in 1991, Jan Brenier proved that if I'm talking about quadratic Wasserstein distance, which means the cost is p equal to 2. And in this case, I can relate the solution to the Monchampère equation. So if I put my source distribution in the numerator and my target distribution in the denominator, and if I also can solve this fully nonlinear PDE, then the solution, the gradient of that solution will be my optimal map T. So this offers us one more way to compute the Wasserstein distance of the optimal map, but also connect us with differential geometry, because the Monchampère equation has already been studied by Weil and the Minkowski problem in differential geometry. And that's also give us a way to investigate the geometric information embedded in the Wasserstein space and for the Wasserstein distance. And another thing that I really like is the connection with the kinetic field. So this famous JKO paper tells us that we can do gradient flow, not only under the traditional Sobolev norm, but we can also do gradient flow under the Wasserstein space. So Fritzsche derivative and the gradient are a little bit different. And it's exactly, we put it into the Wasserstein space, give us different gradient flows. And using those very kinetic rich energy function like entropy plus potential, or interaction energy. And if we dissipate those energy under the Wasserstein gradient, in the Wasserstein space, we get such PDEs who are also at the same time well-known PDEs we know earlier, like heat equation, Fokker-Planck equation, etc. So this offers us one way to study those equations from the variational point of view, but another way for us to try to see what possible applications of Wasserstein distance and optimal transport. So here is a little bit overview, and I'm pretty sure for the rest of the workshop, you can see many different talks target on different aspects of optimal transport. So for me, I want to emphasize what I appreciate the most as the difference between optimal transport and the traditional or the most familiar Sobolev-based norms. So we have two distributions, and they are not the same, and we want to make them the same. So after single rearrangement, they do become the same, and it's our turn to calculate how much effort we made. And the particular different way of capturing these differences really separate the Wasserstein distance from a very major class of distances. It's exactly the amount we move multiply the distance we move. Because LP-based norm only calculate, we're only concerned with the amount we move. But for optimal transport, each point, the two directions, or maybe for higher dimension, it won't be just two, but just two general directions are considered. The domain changes and also the function's range changes are considered. And that's the transport cost for a single point. And we will integrate the entire domain to get the entire transport cost. And this mathematical formulation has a one-to-one correspondence versus my previous slides. F of x is the density function represent how much mass at a particular point x. And f of x really represent how much mass I lift. And x minus t of x is the distance, like how far away I move from x to t of x. And so leave this mass and move that away. This two parts multiply together, give me the transport cost for x. And I integrate over the entire domain, give me the total transport cost for this particular transport map t. And among all the possible map t, I select the one that gives me the minimum cost. And that gives us the Wasserstein distance and also the optimal map. So for the case of p equal to 1, Manhattan distance, and the case of p equal to 2, quadratic Wasserstein distance has been really widely studied. But in my talk, I will particularly focus on p equal to 2. So for my wave inversion problem, if you remember, we discussed earlier in our previous slides that when I do not have the correct velocity parameter, what I see is translation and dilation. So I want my objective function to capture that. So one way for us to theoretically justify why Wasserstein distance is a good candidate of doing that is to prove its convexity with respect to translation and dilation. And here is the setup of the theorem. Consider we have the true or reference signal or reference distribution function G, and G is fixed, and F depends on G in a way that F is a translated and a dilated version of G. And both F and G are functions defined on RD, so the translation can be more detailed, parameterized in terms of every dimension. And the same with the dilation. So dilation can be parameterized in every direction. So these 2D parameters together is the parameter for my translation and dilation, and tell me how F depends on G. So if I want to compare the differences between F and G, I expect no matter which objective function I use, that objective function will be a function of my transformation parameter theta. So what we did was to compare or compute the Wasserstein distance between F theta and G, and we showed that it is a convex function in terms of the multivariable theta, which means it is not only convex when we fixed translation to convex in dilation, or we fix dilation, it's convex in translation. It's really a joint convexity. And that's a very unique property, capture such global, non-local changes. And that this also have certain statistical indication. For example, when we compare normal distributions, the most widely studied distribution in statistics. And when the translation is exactly corresponding to the mean change, and the dilation is exactly the variance change. And this property also tells us that it will be convex in both the variance and the dilation. And this is the theoretical guarantee why numerically we can see radically different behavior and how Wasserstein distance do the job much better than the L2 norm. So here I'm showing an iterative convergence result. The first row is the velocity, which is my model parameter M get updated iteratively. And the second row is the residual, which is the difference between the synthetic and the observed data. Here we formulate it as a data fitting method. So a good indicator that we did the data fitting well enough is to have the differences gone. So we want the residual to diminish. Let's do it again. So both the L2 least square based method and quadratic Wasserstein based method, they start with exactly the same velocity. But that's also the only difference in their entire framework, the PDE-Constrained Optimization framework. The only difference is the objective function and the corresponding gradient. And but they have different convergence paths, and one clearly gets stuck at the local minima because the residual refused to diminish for the later 200 iterations. And the reconstruction is far away from the true Mammoothy model, which is a benchmark for geoscientists and geophysics exploration. And on the second row, we can see the Wasserstein distance convert to the true Mammoothy model. And also more importantly, the data residual is gone. So that's a good sign that we are getting rid of that local minima. And another property is really corresponding to the second challenge I said earlier about least square based method. It's about its sensitivity to noise. And here I want to theoretically justify the quadratic Wasserstein distance is a better candidate to tackle with sensitivity with respect to noise. Here again, G is my clean data, is a reference fixed, and F is a noisy version of G plus some additive mean zero noise. And here I assume my variance to be sigma square, and add the noise in a way that is piecewise constant on this domain or any domain that we assume in the theorem. And so N is a parameter that we will use later. So now we have a clean signal and the noisy signal. And if I compare the least square or L2 norm between F and G, that's exactly calculating what is my variance, because F minus G is exactly delta. So this is calculating the variance of the noise, and the variance of the noise will be order of sigma square. So that's the case when we compute under the least square norm between the clean and the noisy one. The next, let's look at if we change the way we compare Wasserstein distance between F and G. We get a very different estimate. It's order of sigma square over N. So frankly, it still depends on the variance. The bigger the variance, the bigger this estimate is. But at the same time, if variance is fixed, it's divided by N, which means the denser the noise is added, the smaller the Wasserstein distance can see. It's really counterintuitive because the denser the noise, visually, the more we can see the noise. But for Wasserstein distance, it's actually better, it's beneficial because it's less affected by my objective function. And if my objective function in optimization cannot see that noise, and for my optimization, PDE-Constrained Optimization or neural network constraint optimization, my optimization reconstruction won't overfit that noise. And that's good for my reconstruction, and that give me the stability. So that's a very significant benefit. And one way to interpret why Wasserstein distance has such estimate is to think again how optimal transport compare signals. It's always the amount you move multiply the distance we move. So in this case, the amount we move is always the order of variance. That's not something we can change because that comes from the noise. But the distance we move, since it's mean zero noise, so it cancels it out from positive and negative very, very fast. So we do not have to move too much. We can easily cancel it out. And that's why combining these two aspects together, the estimate is small. And we also have corresponding numerical results in the papers. And the third way, or an alternative way for me to interpret why we see such noise robustness from the Wasserstein distance is really intrinsically embedded in its connection with the Sobolev norm. So here at least the two results recently and also 20 years ago about the connection with the with the Sobolev norm. So in 2000, the paper from Otto and Villani, they proved that if we compare two probability distributions, they are very close to each other, and the d pi is infinitesimally small. Then the quadratic Wasserstein distance between these two close distributions will be asymptotically the differences weighted h-1 norm. So the weighting really means that the integration is not with respect to the big measure, it's with respect to the mu that we are comparing with. So this is when the case that we are comparing two things very, very close. But recently from Remy Perrier, he proved a very, I think, very good non-asymptotic connection, which could be relatively harder, is that if I have f and g that are not close with each other, I can still relate it with the h-1 norm. So as long as both two distributions are bounded about by two constants, the same constant C1 and C2, then one can show W2 is exactly equivalent with respect to the h-1, the big measure based h-1 norm between the of the difference between mu and nu. So this asymptotic and asymptotic result tells me in terms of the spectral bias, W2 is almost the same order as h-1. It may not be as better this one, but it's almost the same as h-1. And the slightly difference is here in terms of the weighting part. And for what is h-1 norm? Here is a review what we learn in functional analysis. H, the general space of HS is a space of functions or the space of temporal distributions whose Fourier transform after weighting belong to L2. So another way to interpret what is HS space is really a space of weighted L2 functions. Only if after doing Fourier transform, the weighting still make it belong to L2. And for this particular choice of HS, different choice of S depends on how I choose the weighting. If I choose S being 0, it means I do not want any weighting. And if I choose S being positive, let's look at this semi-norm. If I choose S being positive and Cassi to the power of positive S will be a monotone increasing function. So the bigger the Cassi, the bigger the weight. So that also tells us a strong norm or positive Sobolev norms really focus a lot on the higher frequency component of my data, of my function F. And vice versa, if I use a negative norm as being negative, it's a monotone decreasing function. So I focus a lot on the lower frequency. So h-1, for example, focus along all the lower frequency. And that's also when the frequency, the noise of the, if the noise frequency is high, Wasserstein distance, which has asymptotically the same order spectral bias with h-1, won't see the higher frequency that much, exactly because it's -1 order here. So it has a damping and negative bias. And that's another way to understand why Wasserstein distance is robust with respect to noise. And that also motivates us to go two directions. One direction is to see whether the general HS norm can be utilized as alternative to Wasserstein distance, because sometimes Wasserstein distance for our dimensions could be very difficult to compute. Another direction is, once I understand those spectral bias, can I extend the application of Wasserstein distance to not only wave inversion, but other kind of inverse problem? So that's the work that we did together with Kui Ren from Columbia and Bjorn Quiz from UT Austin. So we start with a simple change versus the traditional least square method. If we have a problem, a linear operator that map my model parameter M to my data G, and this linear operator, we also assume it's smoothing. It has some reason, because for a lot of yield-post inverse problems, the yield-postness come from the smoothing. For example, for redound transform, the smoothing order is 1/2, alpha is 1/2. For wave equation source inversion, the alpha is 1, it's 1 order smoothing. And for Calderon's problem, conductivity inversion, the alpha is 2. So it's really smoothing, and that's why that problem is so difficult. And for Fourier transform and the inverse Fourier transform, the alpha is 0. It's L2 to L2, so we don't do any smoothing. And that's why nobody talk about inverse Fourier transform as an inverse problem. So alpha here is really a parameter how difficult our data matching or our inverse problem is. So with this parameter in mind, and with also the fact that M belongs to the function space H beta, we can try to solve this problem by the traditional inverse data matching problem with a variational approach. I try to find the optimal parameter M by penalizing the difference between the true data G and my synthetic data A of M or F of M, depending on the linearity or non-linearity of the problem. And instead of using the least square norm, we generalize a little bit, go one step forward to think about the HS norm. And earlier we can define HS norm based on its Fourier transform. So it's really, after doing Fourier transform, we weight different frequency differently. And one can expect different choice of S will give me very different reconstruction effect because of this spectral bias. And this is also what I call as an implicit regularization. Throughout my talk, we didn't talk about anything about regularization because I focus on objective function. But this particular choice of objective function already have an implicit bias towards certain frequency, and that embed our assumption. So this is an implicit regularization effect. So first of all, let's look at theoretically what we lose by choosing or going for Wasserstein distance or H-1 norm. Here we have the strong assumption that we can approximate the inverse operator very accurately to a certain degree. This is a strong assumption because most of the time we won't be able to do that. So let's say if we can do that, and we can reconstruct the solution just by applying this inverse operator, then we will get our reconstruction M delta based on this parameter. And the delta means how much noise it gets propagated back to my solution. And once we have that solution, we can do some stability estimate to see how the model parameter perturbation depends on my data perturbation on the right-hand side from the noise. So delta here is really the power of noise. So not surprisingly, the right-hand side estimate depends on both how smoothing my operator is, alpha, and also where my M belong to H beta. And thirdly, also very importantly, which objective function I use to do this inverse data matching. Assume that we do not have any choice for alpha and alpha beta are already physically constrained. Then what we can only choose freely is the choice of S. So here we have a resolution analysis to see how the resolution depends on my choice of S. So here we prove that epsilon will be proportional to delta to the power of 1 over alpha plus beta minus S. Again, this is just constant. Then we see that if we choose a positive S, like 10, S equal to 10 or 1, then delta to the power of that number will give us a very smaller epsilon. So the bigger the S I choose, the smaller epsilon I choose, which means I get better resolution if I go for the positive norms. But reversely, if I choose negative norms, I will have a relatively bigger epsilon, which means I probably don't see that many details. I lose resolution. So this is why I say what we lose when you go for negative norms. You won't see as much details as the positive norms. And that's to be expected. The definition of the negative norms focus a lot on the lower frequency. And especially for linear problem, if your data focus on the lower frequency, your model reconstruction inevitably also will focus on the lower frequency and ignore the higher frequency. So then what we lose is the resolution. And the other way around, let's see what we get if we have high frequency noise. And we look at it from the other point of view. We have the noisy data, and I take a Fourier transform. So what you see right now is just the solution to the normal equation for the HS-based method, or weighted least square based formulation. If I choose S equal to 0, that's exactly the least square solution. And if I choose S being positive, then that's the normal equation solution. So if I choose S to be positive and I happen to have higher frequency noise, again, Xc to the positive power of S will amplify. It's really the bigger the Xc, the bigger the weight. So that part of the noise will be exaggerated by a lot exponentially because of the fact we have a positive S. And then it also will be propagated, get back to my reconstruction at that Xc level. So that's the difficulty, or that's the shortcoming of choosing a positive S. We exaggerate the noise, and the overfitting phenomenon will be even worse. And the next, alternatively, the other way around, let's see what we get by choosing a negative S. So a negative S will have a higher weight in the lower frequency and a smaller weight on the higher frequency. So if my higher frequency has noise, then I won't treat it as importantly as I would do if S equal to 0. So we dumped that part of the noise. And if we dump that part of the noise, that part of information won't be propagated back all the way to my reconstruction. And as a result, my reconstruction at that frequency level won't have that noise input. And that's again, when we go for Wasserstein distance and go for L2 H-1 or H-2 based inversion. And then also we have a numerical example to verify that. So finally, I want to do this numerical comparison to repeat what we gain and what we lose. So this is a very simple example by doing a kernel deconvolution. The fourth row represents the case that my data is totally noise-free. And the fourth column is L2, the middle column is H-1, the last one is W2. So in the noise-free case, one can see the L2 really reconstruct more details than H-1 and W2. L2 can match all those corners reasonably well, while H-1 and W2 just ignore them, have a very beautifully smooth curve. So that's the case what refer to what we lose. We do lose resolution. We won't see those details. But the second row really say the other story. The other side of the story is what we lost. Here is a more realistic setup. Our data now contain noise. Even if only contain 2% noise, the L2-based inversion dramatically be different from the noise-free case. You see a lot of oscillatory features that are wrong, and that's direct impact of overfitting the noise. While H-1 based and W2 based still very robust, even with a 10% noise. It's almost the same as noise-free case. So this is a very good diagram to show what we gain and what we lose by choosing different norms. I wouldn't say one norm is better than the other. Actually, both of them are very important if you think about it from an inverse problem point of view, because through the inversion, I want to achieve both stability and accuracy. And that motivates us to have a hierarchical technique to tackle such problems. Maybe at the beginning, you want to use negative norms, or you want to focus on more on the lower frequency, especially for nonlinear problems. You'll have the local minima concern at the same time. And we focus on the lower frequency mode, and the low frequency mode have a bigger basin of attraction. So we also have less risk get stuck on local minima. And as my inversion progress and stably progress, and I also need to focus on accuracy, so we can transform gradually from coarse to fine level. And that's why in, for example, Turing's thesis and also many other inverse problems, including wave elliptic equation, curl EM and inverse scattering, and many others, you can see this frequency bias. And this frequency biased or dynamic way of doing that give us the best result. And this way can not only use as data misfit, measure of residual in forward problem, and even can be used as likelihood function in Bayesian inversion. And that's the work I had with Matt Dunlop. But I don't think I have time to finish that. And I would like to jump to my conclusion. So we start with the property of Wasserstein distance because of its convexity, very nice convexity in terms of translation and dilation. And we also realize it has high frequency noise robustness. There are two ways to understand that. One way is the particular way Wasserstein distance compares stuff. Another is really its spectral connection with Sobolev norms. And that's also make us to go forward to understand certain imaging techniques and why and how they work. And there are metrics even beyond the W2, and that's why I highlighted. We don't have to constrain it really inside optimal transport. But for example, Sobolev norms that are easier to compute, and also next we will have this MMD also capture the global information. So the studying of optimal transport really helped me to gain the insights, like what kind of property will work and will work for what kind of problem. So the convexity of W2, again, if that's the part of we focus on, it's not just limited to hyperbolic equation inversion. We also show in the paper with Kui that it can be used for diffusive environments and to reconstruct from projection and reconstruct from highly localized sources. Also, all such parameter and data interaction also give us something translation and dilation based. So this is the end of my presentation. Thank you very much for your attention.
Thank you. Very interesting and intriguing talk. The way that we are going to proceed is let us kind of address kind of a few general questions from the audience, and then after that we can go to the discussion rooms, right, and continue kind of discussing, or we can stay in the main Zoom meeting for the somehow next meeting. So you can, now given that we're stopped, if you want to ask a question, you can, either just raise your hand, or you can just start. You can just speak up, and we'll proceed like that. Right. Well.
Okay. Hi.
Yeah. Go ahead.
Yeah. Thank you. So, thank you very much for this very nice talk. A lot of ideas to digest. So I'm just everything. Yeah, I have a question with regard to your proposal. I think it's very interesting, and you mentioned that it can be employed into a Bayesian context.
Yes.
Like a likelihood function, right? So
yes.
I work on data simulation, where we have prior from numerical model, and then we employ some sort of L2 norm in the likelihood function to compare.
Exactly.
Yes. Model states. So do you think that it is possible to take this framework and put everything into, for instance, a Hilbert norm context?
Yes,
they are robust. You can exploit the smoothness of L2 norms and
definitely. So
the robustness of L1 norms. Yes.
If you look at slides now, this is what we my joint work with Matt Dunlop from Cront. So we summarize a little bit of different choice of likelihood function, but they are very representative. You definitely can expand this table by a lot. So if you use the L2 norm, it means the underlying assumption, noise assumption is additive Gaussian by noise. And if you use the H-1, especially H semi-norm, H-1 semi-norm, it means you still have additive noise, but your covariance matrix involves elliptic operator. And if you have positive norm, I can assume this will be inverse elliptic operator. So this is the fine differences. So this second line really can generalize to the general Sobolev norms. And if you use W2, we prove that it will be a multiplicative noise, but it's state dependent. So it's it's more general. And also we can see from the nonlinear way we define Wasserstein distance.
I see. Okay, thank you.
Any other questions? Well, I have a couple, right? So I really like somehow your analysis on the simple case that you had with Bjorn saying, okay, for different levels of smoothness, right? This is the error and robustness that we can obtain. But if we look at somehow, I was wondering somehow going kind of a little bit investigating if you have the same level of smoothness. So let's say you look at the H-1 and you look at Wasserstein, right? They are at the, they would be on the same level of smoothness, but they have somehow different properties. Namely, if you compare, and just like you had, if you compare an image and its translation, the way that this is going to scale with distance is going to be different. And even more importantly, perhaps geometrically, right? If I look at what are the, in Wasserstein, you can look at the geodesic, and then you can look at the midpoint of the geodesic is somehow your average, your Karcher mean, right?
Yeah.
And then you would see that, I mean, between two transits, you get the same thing. Whereas for H-1, you still get a linear interpolation. So what would guide your choice in deciding what is a good metric if you're, let's say, at the same level of smoothness? What is your preferred?
I totally agree. We have really definitely thought about that because we can see certain, for example, just geodesic for Wasserstein distance is clearly this translation. If I have two Gaussians, it's just a horizontal move. And the geodesic for H-1, even it's two Gaussians, it will be like very, very classical L2 based or Sobolev based. So this is very different. And I think what we showed this part with the analysis result really just show the distance part. It means the distance, the value scalar has this dependency, but it doesn't mean the locally gradient will also have this dependency. So both this result, these two, only show the distance are related, or the absolute value of that scalar, that normal distance is related. But it doesn't say anything about the gradient. And it's the gradient that matters, that give us either a translation horizontally or like delete the mass and create the mass. And that's what I think it's a very fundamental difference for that another point of view. In terms of how we use that, I think from my understanding of the global change, which is global translation, it will really improve the optimization landscape of the problem. Because the translation
like what
dilation.
You had at the beginning.
Yes, it will really help in, and that's the part that H-1 cannot. So for example, if we talk about H-1 for 2D functions, it won't be convex in terms of translation. But if we talk about 2D functions, the distributions under Wasserstein distance, it will be always convex in translation. So those global features are still the benefits of W2 that cannot be replaced.
Thanks.
Dayan, can I ask something? Sorry.
Yeah, go ahead.
Hi, Carla.
Hi, good to see you.
You did.
Very nice talk, by the way. I came a bit late, but what I saw was super exciting. Thank you. So I mean, now that you're showing this result here, I guess this is also one of the main motivations why you use W2.
It's a little bit different. Just after I do W2, I realize this result. Yeah.
So what about other WPs?
So the only one that I'm a little bit more familiar with, not that familiar, is W1. I think for W1, there's also very nice property, but may not be with H-1, may not be with L2 based Sobolev norms. I think it has certain property with total variation or bounded variation, that kind of space. And in terms of smoothing, I'm not very sure about smoothing, but the global convexity that I mentioned earlier, in terms of translation and dilation, still remain. W1 still have that. So if we compare shift translation, W1 will still be convex. So that's the part I know. But in terms of smoothing, from my own intuitive way, it's like more related. W1 is more like L1. So it can help us to do denoising, but really on the keeping the edges side point of view.
Okay, so you have not you stuck to W2 for what you wanted to do. I understand. Yeah.
Yeah, I like the connection with so I start with the Marshall-Ampere equation to solve. So there's a lot of connection in that area.
Thank you.
So let's give the Gather Town a try. So I'll send a link in chat. I mean, Daniel, he emailed us the link during the talk, but I also just sent it in the chat. So so we have two options. You can either go to Gather Town, which I'm also going to do in a minute, and let's see how it works and continue discussing there. And also remember that the next talk will continue here. So Carola will be talking at 10:40 Central Time, so in about 15 minutes. So by that time we should come back. So okay, so I'll keep this meeting, right? But I'm also gonna follow the URL link and see what happens.